Hello everyone, welcome to my channel AWS Solutions Hub. Today we are going to see a use case, or we are going to build a use case based on AWS Bedrock. So we are going to build a PDF chatbot using RAG and AWS Bedrock. We are going to divide this video into two parts. In part 1, I will explain you the architecture that we will be building as a part of this use case, and in part 2, I'll show you the complete code how to do it using AWS Bedrock. AWS Bedrock is a fully managed service that makes it straightforward to build and scale generative AI applications. Amazon Bedrock offers a choice of high-performing foundation models from leading AI companies, including A121 Labs, Anthropic, Cohere, Meta, Stability AI, and Amazon through a single API. It enables you to privately customize foundation models with your data using techniques such as fine-tuning, prompt engineering, and RAG or retrieval augmented generation, and build agents that run tasks using enterprise systems and data sources while complying with security and privacy requirements. Before we start our use case, there are some components I feel you should know. Background on large language models and retrieval augmented generation RAG. Large language models utilize a technique called pre-training on massive text and datasets like the internet, code, social media, and books. This allows them to generate text, answer questions, translate languages, and more without any task-specific data. However, their knowledge is still limited. Retrieval augmented generation enhances LLM or large language models by retrieving relevant knowledge from a database as context before generating text. For example, a financial advisor LLM could retrieve a client's investment history and profile before suggesting financial recommendations. So RAG is on top of large language models. Large language models utilize a technique called pre-training. So they are already come with pre-trained. But when you need a user specific response, we go for retrieval augment generation. Retrieval augmentation combines the benefits of large language models, ability to understand language with relevant knowledge in a domain specific database. This makes RAG systems more knowledgeable, consistent, and safe compared to vanilla LLMs. So, if you don't want to use RAG, then you need to fine tune large language models. You need to train large language models. So, when a user makes a query, user need to receive relevant information. If large language models are not trained enough, then user will get a not specific answer to his query. So if we don't want to go for the fine tuning of the large language models because it is not straightforward, then the RAG or the retrieval augmented generation which comes in picture, where we keep some knowledge databases, and using those knowledge databases and large language models combinedly we give response to user. How to do that we will see as a part of demo. Next, let's understand the RAG advantages over fine-tuning of the large language models. Fine-tuning adapts a pre-trained large language model to a specific task by training it on a domain-specific data. For example, a pre-trained LLM can be fine-tuned on financial documents to improve its finance knowledge. However, fine-tuning has several downsides compared to retrieval augmentation. For example, forgetting. Fine-tuned models often forget to or lose capabilities from pre-training. As an example, a finance fine-tuned LLM may no longer handle general conversational tasks well. Training data dependence. Performance is entirely reliant on the quantity and quality of available training data. Collecting high quality data is expensive. Lacks external knowledge. The model only knows what's in its training data and lacks real world knowledge. No customizable. Changes to fine tuned model require retraining, which is expensive. So, as I said, if you don't want to go for RAG and you want to fine tune LLM, these are the challenges you will face. You need to keep on adding data to LLM, make it more relevant to your user queries. Otherwise, the user will not have the right response. Whereas in contrast, RAG systems retain capabilities from pre-training since the LLM itself is not modified. Augment the LLM with customizable external knowledge sources like database. So, before we pass query to LLM, we augment the data. We divide that data into vectors, or for example, at this moment, let's understand we divide that data into chunks. Allow changing knowledge sources without retraining the LLM. Okay, so in RAG, we do not touch to the LLM part. We create one vector database where for the chunks of data sets, we take relevant information from those chunks of data set, and with user query, we send it to the LLM. Have lower data requirements since the LLM is not retrained. Therefore, RAG systems often achieve better performance than fine tuning while retaining more capabilities of the original LLM. Key components in RAG implementation. First, foundation models. Foundation of RAG architecture is a pre-trained language model that handles text generation. So, as I said, we are going to use the Amazon Bedrock, which already encompasses models from the leading AI companies, Meta, Anthropic, Amazon, that possesses strong language comprehension and synthesize abilities to engage in conversational dialogue. Vector store. At the heart of retrieval functionality is a vector store database persisting document embeddings for similarity search. To make it more simplified, in this use case, user is going to upload a PDF document where we are going to divide that PDF document into small chunks, and those chunks will be stored into vector database as indexes. How we will do that, we'll see in the demo. But just make a note, there is something called the vector store where the data gets stored. Retriever. The retriever model uses the vector store to efficiently find pertinent documents and passages to augment the prompts. So retriever model basically retrieves the data from vector store. Embedder. To populate the vector store, an embedding model encodes source documents into vector representations consumable by retriever. Models like Amazon Titan embedding G1, and this is the one we will be using during our demo. So the embedder will make sure that PDF document is chunked into small chunks and stored into the vector store so that retriever can retrieve it. Then the document ingestion. Robust pipeline ingest, pre-process and tokenize source documents, chunking them into manageable passages for embedding and efficient lookups. So we are going to again use Langchain framework, where how to chunk the data. Okay, how do we divide that data? That is something we will see in Langchain framework. So as I said, we will build this use case using all these concepts components I just discussed, and we will be using AWS Bedrock, we will use Langchain, we will use Amazon Titan as the embedded model, and we will see a complete use case built in part 2. So I'll show you how our architecture will look like, what all components are involved, how the user transactions will happen between the different components. So let's understand that first, which will help us to understand how our application is built in part 2. We are going to build a complete POC, what all components are involved. Uh, so let's start. First and foremost, okay, we need a data store or a knowledge base, and here we will be using, let's say we will use S3. Okay, S3 is our knowledge base. Okay, and when the PDF is uploaded onto the S3, okay, we will, again there will be multiple PDFs are uploaded, so for every PDF uploaded, that PDF will get converted into the chunks. Okay, so let's say this is converted into different chunks of data. Okay, how this is done? This is done using the um, embedding model. Let me draw it the better way. Embedding model. Okay, so let's use the same ink. Okay, so this is our first transaction. Okay, this will be second. So PDF is uploaded. Okay, then it is converted into chunks using the embedding model. Okay, the embedding model converts this data into vector. Okay, vector is nothing but, it is basically a representation of some numbers. Okay, in the format it can be stored into the vector store. Okay, and there will be a vector store, okay, which stores all these vectors in indexing. Okay, so indexing is done and data will be stored here. Okay, so let's say this is how the indexing is done and the data is stored. Okay, using indexing the data is stored here. Okay, now let's understand it from the user end perspective. So this can be a journey for the admin, where admin is keep on adding the knowledge sources into the knowledge database, and those knowledge database is getting converted into the indexing and stored into the vector store. So this is our vector store or vector database, if you want to call it. Okay, let's understand the journey from the user end perspective. Okay, so this is our user, okay, who has some interactive prompt, okay, with submit button. User will put a query and it will click on submit. That query will come to embedding model. So let's call it as transaction 4 from the user perspective. It will come to the embedding model, embedding model will convert it into vector. Okay, let's say one. Again, it is a representation of some numbers. And okay, what it will do, it will try to search a nearest vector, will try to see a nearest neighbor search available into the vector store. Okay, so let's say this is the data set, okay, which matches this vector. Okay, so this will be returned. Okay, so this is returned from the vector store. So we have context from vector store. We already have a query from user. Okay, this combination of query and the vector store data is given to LLM to generate a user specific response. Okay, once this is done, so let's call it user transaction 6, 7, 8, and once the query reaches to LLM generates a response. Okay, LLM generates a response which is passed to the user as a answer to his query. Okay, so this is how the complete architecture will look like. How to do it, I'll show you the complete code, how I do this complete POC, and you will have a complete picture or this complete architecture converted into a code. Okay, so let's see that as a part of the, like, basically as part 2. I'll upload that video. Okay, um, so hope you have understood this complete part 1. I have tried to explain the different components involved into RAG, what is RAG, and difference between fine tuning the LLM, why do we go for RAG and not just do the fine tuning of the LLM, and in this use case what all these components, how they are involved. Okay, so I'll see you in the part 2, where I'll show you the complete code for this POC. Thank you, thanks for watching, bye.